Hi everyone, welcome back. So in the last lecture, we were discussing power of adjacency matrix, and we have seen this result that the power of adjacency matrix will give you number of walks between every pair of vertices. So this result we have already seen, and this result we are going to use, but this is very important result that whatever graph you take, okay, so you can have any graph. So this is something interesting, or I can say important, that you can have any graph. uh, you can have any graph, whether directed, undirected, it does not matter. Okay, you can have basically directed graph, digraph, or undirected graph. So any graph that you have, so you can have any graph G. Now let's assume for this G, let's assume this adjacency matrix you have, this adjacency matrix that you have, that is M. Then in this situation, what your M power K tells you, if you do the M power K, this M power K tells us the number of walks, okay, the number of walks of length exactly K, number of walks of length exactly K. How many walks are there of length exactly K between every pair of vertices? Okay, between every pair of vertices. So this we have already seen in the last lecture, and the proof we have seen, basically not the complete proof, but I told you the idea of the proof we have seen, and you can continue with the induction and you can prove it. Okay, so basically the idea we have already seen why, like this M square we have seen, that this M square will give you the number of walks of length exactly 2 between every pair of vertices. Okay, that we have already seen. Similarly, you can use the induction and you can prove for M power K. So but anyway, that is not required. So whatever we have seen, that is enough in the last lecture, and some questions we have done. That M power K, this M power K, this is very important thing. This M power K will tell us how many walks are there of length exactly K, okay, between every pair of vertices. Now let's see some applications of that. Let's start with the first application. Can you find degree of all the vertices in under undirected simple graph? Can you find degree? I want degree of all the vertices in undirected simple graph. Tell me, how will you find? What is coming to your mind? What is the method one? Undirected simple graph you have. So you have undirected simple graph. Simple graph means there is no self loops. So you have undirected simple graph, okay, and you want to find degree. Find a degree of every vertex. Then what you will do, tell me? Find degree of every vertex. What is the idea of one number one? Yes, very good. Okay, so degree of every vertex, if you want to find, then idea number one is this. So I can say idea one. What is the idea one? Idea one is this, that just in the adjacency matrix, for every vertex you find how many ones are there. Yes or no? Correct? Like very simple, that in this adjacency matrix, for every vertex, whatever vertex you have, for this vertex you find how many ones are there in this row. Just count number of ones. Okay, so in this row, if you count number of ones, so number of ones that you have here, number of ones is the degree of D. Yes or no? Is the degree of this vertex V. Like you have some vertex V. So if you have this vertex V, then that is degree of vertex V. Is this clear? This is the idea number one. Agree or not? Very simple. That what you do, you count the number of ones. How many ones are there? That is the degree of number of ones, is basically the degree of V. Very simple. What is the idea number two? What is the idea number two? See, idea number two is something like this. You tell me M square. If you do M square, then what your diagonal entries are? A simple question I am asking. A simple question. You tell me in M square, what are the diagonal entries? What diagonal entries tell you? What diagonal entries tell you? What the main diagonal entries tell you? Can you tell me what the main diagonal entries tell you? Entries tell us. Let me know. In M square, you have undirected simple graph. You have undirected simple graph. You have undirected simple graph. There are no self loops. Mavit, you have undirected simple graph. In this graph, if you find M square, what the main diagonal entries will tell you? In this M square, what this will tell you, like in this M square. So you have undirected, your graph is undirected. Also, your graph is simple. This is your graph. Okay, this is your graph. In this graph, if you find M square, adjacency matrix is M. You find M square. In this M square, you tell me what this entry will tell you. Like you have V here, V here. What this entry will tell you in M square? What this entry is going to tell you? What this entry will tell you? It will tell you number of walks of length 2. In undirected simple graph, how many walks of length 2 you can have? Just think about it. You have some vertex. In undirected simple graph, tell me, undirected simple graph, there is no self loop. Undirected simple graph. So how can you have walk of length 2? How can you have walk of length 2? You can have walk of length 2 if and only degree, because of degree. Yes or no? Agree or not? Like you can see like this. Because of this degree, because of this, like you will get walk of length 2. You will get walk of length 2. You will get walk of length 2. So this entry will be 3. This entry will be 3 or not? Like walk of length 2, walk of length 2, walk of length 2. Okay, walk of length 2, walk of length 2, walk of length 2. So this entry will be 3 or not? So this is degree or not? This is degree of V or not? Let me know. Is this clear? So very simple. This first application, is this clear? The first application is that, okay, just you have undirected simple graph, just find M square. Okay, just find M square. Find M square, and in the M square, this is what you find. You find M square, and in this M square, you can notice the diagonal entries are the degree of all the vertices. The main diagonal entries, the main diagonal is giving you what? The main diagonal is degree of all the vertices. That's it. So, can you tell me, did you understand? Please tell me yes or no. Did you understand that? Find M square. In this M square, the main diagonal is basically the degree of all the vertices. In M square, this is what you do. Just find the M square. Okay, all you have to do, just find the M square for this graph. In this M square, you can see that, look at this entry, A1, A1. What this entry will tell you? This will tell you degree of A1. This will tell you degree of A1. Like this is AK, this is AK. Okay, so this will tell you degree of AK. This will tell you degree of AK. Clear? This is the first application. First application is clear. Something tricky I will ask you. I will ask you something tricky. Okay, the first application is clear. Then you tell me, what is trace of M square? You have simple undirected graph. You have undirected simple graph. Undirected simple graph. You tell me, what is trace of M square? What is trace of M square? Tell me. Simple question. What is trace of M square? Trace basically means what? What is trace? In the what is this trace? This trace is a summation of main diagonal entries. Sum of main diagonal entries. Sum of main diagonal entries. So tell me what this trace will tell you. So this trace will tell you what? This will give you the summation of all degrees, yes or no? array, yes or no? This will give you summation of all degrees. And that is equal to twice the number of edges. So the trace is equal to twice the number of edges. This is interesting. This is a simple question, isn't it? Isn't it simple question? Very simple question. But in the GATE exam, this also looks very heavy. Yes or no? In the GATE exam, this question also looks very heavy if this option is given to you. Correct? This is a simple concept, extremely simple concept. You can prove it that if you have a G, which is undirected simple graph, okay, and for this G, the adjacency matrix is A, then you can easily see that this will happen. Trace of A square will be equal to this. Very simple. So that's it. Now let's move on. Now let me ask you something interesting. What if you have undirected graph with self loops? If you have G which is undirected but may have self loops, G is undirected graph which may have self loops, okay. Now how to find degree of every vertex? How to find degree of all vertices? Now, how to find degree of all vertices? So can you see this? You have undirected graph with a self loop which may have self loops. Okay, then how to find degree of all vertices? Two options I am giving you. Option number A, option number B. You tell me the answer. Okay, the option number A is basically just m square. Okay, or basically what you do, sorry, how to find total degree of all vertices? How to find total degree means total degree of all the vertices. Simple question, but you think about it. Like Mavit is saying that in the GATE exam, it is time taking. Now you apply your thoughts and you tell me the answer. I am giving you options. How to find total degree, how to find. Okay, so let's see this. Now I am giving you some options. So the first option is that is trace of A square, or I can say trace of M square. Adjacency matrix is M. Adjacency matrix is M. Now you tell me that will be trace of M square. That will be trace of M plus M square. That will be trace of 2M plus M square. That will be trace of okay. So these are the four options. I should put this question in the test series. These are the four options, and I want your correct answer. I want the correct answer from you. So you have undirected graph which may have self loops. Adjacency matrix is M. Then what is the total degree of all the vertices? Total degree I want. Total degree of all the vertices. What is that? So you tell me, first of all, like if you have A, B, C, something like this, and you have self loop, what is the degree of A? What is the degree of A? Tell me the degree of A. Degree of A will be what? That will be 4, right? Because of self loop, you have to count 2. Okay, self loop counts 2. Yes or no? Self loop counts twice. Self loop counts twice. Now you tell me the answer. Self loop counts twice. Now you tell me the answer. If this question comes in the GATE exam, what you will do? If this question comes in the GATE exam, what are you going to do? You can take a simple example like this, correct? This example you can take. Okay, take a small example. If this question comes in the GATE exam, you can take a small example. So let's solve this from the GATE exam point of view. Let's assume you are in the GATE exam. Can you solve it by taking this example? Can you quickly solve it? Take this example and quickly solve it. Take this example. So for this, what will be M? M is quite simple. M will be like, that will be 1, 1, 1. Okay. So ABC, ABC. So like from B, you can see that will be 0, 1, 1. And from C, that will be 0, 1, 1. Okay. So this will be M. This is your M. What is M square? M square is number of walks of length 2. Number of walks of length 2 from A to A. From A to A, there are 3. From A to B, number of walks of length 2, remember. From A to B, how many? There are, from A to B, there are 2. From A to C, there are 2. Okay. Next, you can see this is your M square. Like from B to B, there are 2. From C to C, there are 2. From B to A, there are 2. Okay. From B to C, there is 1. From C to B, there is 1. From C to A, there is 2. Okay. So now you tell me the answer. You have M square. In this question, what is total degree? In this question, what is total degree? The total degree is 4 plus 2 plus 2. So the total degree is basically 8. So your answer must be 8. So can I say this option is correct? Can I say this option is correct? Trace of M square? Can I say trace of M square is correct? Can I say? So this option A is definitely not correct, right? Yes or no? This option A, this is definitely not correct. You can see that. So definitely option A is gone. Okay, what else? What else is gone? What about this trace of 2m plus m square? What about this one? Trace of 2m plus m square. 2m plus m square. Like what you do, you multiply with 2. Okay, the trace of that. You multiply this with 2, then you add in this. So that will be like, I can say 2 plus 2, that will be 4 plus this. So that is also not correct. This is also gone. Trace of m plus 2m square. This is also gone. Trace of m plus m square. This is correct. So this is how you can solve in the GATE exam. In the GATE exam, this is how you can solve. But this is not analysis. Yes or no? This is definitely not analysis. This is how you can solve in the GATE exam. You can take a small example and you can solve in the GATE exam, but this is not analysis. Okay. This is how the coaching institutes will solve. In Go classes, we don't do this. Okay. So definitely, like in some coaching institute, they will solve like this and the student will become very happy. A student will feel very happy that, wow, what a teacher, what a god. Okay. The question is solved within 2 seconds. He is a god. Okay. So they will solve like this. They solve every question like this. In every subject, theory of computation, any subject you take, they solve all the questions like this. But anyway, this is not an analysis. Let's do the analysis. You tell me a simple question I'm asking, that you have a graph G, which is undirected graph. Okay, this is an undirected graph. May have may contain self loop. May contain self loop. Now you can easily see that in this G, there is an adjacency matrix. The adjacency matrix is M. Now what you do? Now you can notice in this G, you can have self loops. For example, you can have this type of loops you can have. Okay, this type of self loops you can have, as you can see. Now you tell me, If you find, first of all, you want to find the total degree, right? Okay. To find total degree, you can easily see that this self loop will give you, from M, you can get 1 degree. Yes or no? Correct or not? From this M, this main diagonal, what is the trace of M will give you? See the trace of M. This will give you this will give you, basically, this will give you number of self loops. Yes or no? Can I say? It will give you number of self loops. Can I say this? This trace of M will give you number of self loops. How many self loops are there? Okay. You tell me what this trace of M square will give you. This trace of M square, what it will give you? Trace of M will give you number of self loops. What trace of M square will give you? See, trace of M square will give you like as usual, but because of the self loop, what you are going to get? See, you can notice, look at the trace of M square. Only the main diagonal. From A to A. From A to A, you will get 2 values. Yes or no? Are you getting my point? So this trace of M square, what it will give you? It will give you basically, it will give you total degree, but self loop counted once. Very good. Alap, very good. So this will give you total degree, but self loop counted once. It will give you total degree, but self loop counted once. Isn't it? But self loop counted once. Please tell me, did you get this? Because focus on trace. Trace means main diagonal. Focus on main diagonal. Focus on main diagonal. So just focus on main diagonal. You can notice that this main diagonal will give you degree, but self loop will count only once. But how many times we have to count the self loop? How many times we have to count the self loop? 2 times. So what we can do, we can just add them. So the answer will be, I can say total degree will be what? Total degree will be, you can do trace of M plus trace of M square. That's it. Or you can do trace of M plus M square. Or you can do trace of M plus M square. Both are correct. So the total degree that you will get will be trace of M plus trace of M square. Or you can say trace of M plus M square. Both are correct. This is also correct. This is also correct. This analysis, did you understand? Please tell me. Did you understand this analysis? Okay, so very simple analysis. You can see that like you have this graph A, B, C, D. Let's assume you have this graph. You can easily see that trace of M, what it will give you? Trace of M will give you 2. And what trace of M square will give you? What trace of M square will give you? That will give you degree, but all self loops will counted once. So it will give you 1 plus 2, 3. 3 plus 4, 5, 6, 7, 8. So it will give you 8. Okay, so basically self loops counted once. Why this trace of M square is this? Because you can easily see that from A to A, how many walks? Tell me number of 2 length walks. How many 2 length walks from A to A? Tell me, from A to A, how many 2 lengths walks? So that is 1 here, 2 here, and 3 here. So that will be 3. Okay, from B to B, how many? From B to B, how many? 2. From C to C, how many? That will be 2. From D to D, how many? That will be 1. If you add them, then that will be 8. Trace of M square is 8. So self loops are counted once. So finally, I can say total degree will be what? I can say total degree is equal to trace of M plus M square. This is your answer. That's it. So application number 1 is done. Should we go to application number 2? Application number 1, was it easy? If you think about it, was it easy? It was easy, right? You know the property of adjacency matrix. You know what adjacency matrix gives you. So in the option, if something is given, you can handle it. Application number 1 is done. Okay, now let's see application number 2. Application number 2 is find the distance between two vertices in directed or undirected graph. Okay, whether you have directed graph or you have undirected graph, how can you find the distance between two vertices? So this is also very easy. This is also quite easy. You can see that. Just tell me, like, let's assume you have a graph, and this graph can be anything. This graph G you have, and adjacency matrix that you have, that is M. Adjacency matrix is M. You tell me, you are doing M power 1 and the entry is 0. Like, let's assume in this M power 1, between vertex A and vertex B, the entry is 0. Then what it means? In this M power 1, between A and B, this entry is 0. What it means? What it means, tell me. It means there is no walk of length 0, right? Sorry, there is no walk of length 1, correct? We don't have any walk of length 1. Yes or no? Okay, in M power 2 also, this entry is 0. This entry is 0. What it means? What it means? Tell me. It means, again, there is no walk of length 2. See, this is telling you there is no walk of length 2, length 1 between A comma B. There is no walk of length 2 also. In M power 3 also, this is 0. In M power 3, this is also 0. Now what it means? No walk of length 3. Suddenly, M power 4, this value becomes non-zero. I don't know what this becomes, but this becomes non-zero. This value becomes non-zero. Suddenly, this value becomes non-zero. So now what can you say? Suddenly, this value becomes non-zero, means there is path. Between A comma B, there is at least one walk. Now you tell me the distance. What is the distance? Distance means length of shortest path. So tell me now, what is the distance between A comma B? Can you tell me? Now can you tell me the distance between A comma B? That will be 4, right? Yes or no? Very good. So you can easily see that distance will be how much? So distance between A comma B will be is 4. Is this clear? See, very simple. Another simple application. That suddenly it become non-zero. This value suddenly became non-zero. It simply means for the first time it became non-zero. For the first time it became non-zero. It simply means that there is a distance, the distance, because this is the shortest path between A comma B. This is the shortest. Distance means shortest path, correct? Distance means shortest path. So the shortest path has the length 4. But remember, this value must be minimum, right? For example, maybe this can happen. See, you have a graph G. Okay, this is your graph G. And let's assume this happens that M power 5, I tell you that M power 6 or maybe M power 7. In M power 7, also this happens. Let's assume this is non-zero. Then can you say 7 is the distance? Then can you say 7 is the distance? Tell me. Let's assume M power 7. This can I say distance is 7? In this situation, can I say distance between A comma B is 7? This is no. Okay, this is wrong. Why this is wrong? This is wrong because this must be the smallest value, right? What is the first time you got this non-zero? Correct or not? Okay, so you can easily see that maybe this is non-zero, but you can notice still the distance will be what? Still the distance will be this M power 4 only. Okay, I don't care what is this non-zero, but the first time when you got the non-zero, that is the distance. Is this clear? So you can notice distance is still the same. Distance of A comma B, that is 4. Why? Why? Because you can easily see, because the minimum value is 4. Okay, because the minimum value was 4. Yes or no? The minimum value was 4. So this is what I want to say. So you can easily see that n is the smallest. This n is the smallest such that a power n is non-zero. A power is positive. Then this n is the distance. This n will be called the distance. So is this clear? Let me know. Let me tell you, like you have any graph. Again, I am telling you, just let's see this example. Let's assume there is a graph. And for this graph, I am telling you, look at this entry a comma j. Okay. For this graph, you have the adjacency matrix is M. Okay. Now I am talking about this AJ entry, this a comma j entry in this. So this data is given to you. Okay. Some data I give to you. The data is this, that entry AJ, this entry, entry a comma b, this entry a comma b in m power 1. Okay, let's assume a comma b are different, because if they are same, then what is the distance? If they are same, then what is the distance? If they are same, then what is the distance? The distance will be 0, right? Yes or no? If they are same, then distance will be basically 0. Okay, so I am giving you this data that. Okay, let me. Okay, if you do m power 0, what it will give you? What m power 0 will tell you? Any matrix power 0. What is that? Any matrix power 0. What is that? That is your identity matrix, right? Yes or no? That is the identity matrix. And you can notice this will give you how much? This will give you walks of length 0. It will give you walks of length 0. Walks of length 0, that is the trivial walk. Yes or no? Walks of length 0, that is the trivial walk. Means don't stay as where you are. So this is also something important, that if you have any graph, and for this graph, let's assume this is your graph A, B, C. Then tell me how many walks of length 0 from A to A. How many walks of length 0 from A to A? Walks of length 0. That will be 1. Walks of length 0 from A to B, that is 0. Walks of length from A to C, walks of length 0, that will be 0. But walks of length 0, that will be 1. B to B, that will be 1. From C to C, that will be 1. So you can see that if you have m power 0, that will give you walks of length 0. And that will be your identity. So anyway, what I'm saying, this data I'm giving you, m power 0, this entry is, let's assume 0. In m power 1 also, this entry is 0. In m power 2, this entry is 0. In m power 3, this entry is 5. In m power 4, this entry is 0. In m power 6, this entry is 2. Now tell me, what is the distance? Now you tell me the distance between A, comma B. What is that? What is the distance between A, comma B? That will be 3. Okay. That is going to be 3. This is going to be the, because this is the smallest value where you are getting non-negative number. Non-zero number. So this is your application, that n is the smallest number such that this a power n is, in this n power a power n, I can say this element I comma j is non-zero. Then that is the distance between I comma j. Should I move on? This application number 2, is this clear? All the applications that we will see, okay, total 8 applications we will see. Out of these 8 applications, 4 applications have already come in the GATE exam. 4 have already come in the GATE exam. 4 have already come, and 4 may come in the GATE exam. So total 8 applications I found on the entire internet. Yes, 4 applications came in the GATE exam in a single year. In a single year, all the 4 applications came in the GATE exam. But total 8 applications we will see. Now, let's move on. Let's see the application number 3. What is that? Application number 3 is to determine whether or not undirected graph is connected. You have undirected graph. How can you say that is connected? So what is the idea number 1? You can use the adjacency matrix to determine whether graph is connected or not. Okay, whether undirected graph. I'm talking about undirected graph that is connected or not. What is the idea number one? Method number one. Tell me, what is the method number one? What is coming to your mind? How can you use adjacency matrix? How can you use the adjacency matrix to find out whether undirected graph is connected or not? What you will do? Mavit, if you don't have all one entries, then can I say it is disconnected? Mavit, in the adjacency matrix, if you don't have all entries as one, can I say it is disconnected? No. So that is not correct. Tell me, if you have how can you use adjacency matrix to determine whether a graph is connected or not? Determine an undirected graph. Considering undirected graph, it is connected or not. So what will you do? M square equal to M. No, that is also not true. That is also not true. M power n minus 1. Case that is almost true, but case that will also only give you n minus 1 walks, length of n minus 1 walks. That is also not correct. This is the idea. See, what you can do? Method number one, what you can do? Just calculate. Just see M. What to do? Just see M power n 1 plus M power 2 plus M power 3 and so on plus M power n minus 1. You do this. In this, what should happen? In this, what should happen? Tell me. In this, what should happen? Please tell me. In this, what should happen? If it is connected, then in this, what should happen? If it is connected, then in this, what should happen? Tell me. I am talking about undirected graph. If it is connected, then in this, what will happen? Then in this, all entries will be 1. Yes or no? In this, all entries are 1, implies connected. Yes. Implies connected. In this, if all the entries are 1, then it will imply connected. Correct or not? So here, what is this n? This is the number of vertices. This is the number of vertices. So you can easily see that so in this, if all entries are 1, then what you can say? Then you can simply say that it is connected. Okay, and you can also say that if it is connected, then it will be happen. It is if and only if. Yes or no? If it is connected, then this should happen. If the graph is connected, then this should happen or not? If the graph is connected, then definitely it should happen that you must have at least one walk of length 1 to n minus 1. Sorry, all entries non-zero. Sorry, all entries non-zero. So all entries must be non-zero. What should happen? I can say all entries non-zero. You must have all entries non-zero, then it will be connected. And if it is connected, then all entries will be non-zero. Very simple. You can do this. Okay. So this is a simple idea that just find out how many walks are there. Okay. From 1 to n minus 1. Just see this. I am talking about undirected graph here. This undirected graph I am talking about. Okay. So Mavit is saying that every entry has value. No. Number of walks can be anything. Mavit, did you notice number of walks can be 28? Only 5 vertices, 7 vertices. Number of walks can be 28. The particular value can be anything. Is this clear? Particular value, number of walks can be anything. Number of walks between 2 vertices, that can be anything. Like we have seen this example where you have 28 walks. M power 4, 28. In the last lecture, we have already seen. So between 2 vertices, number of walks can be very, very large. Okay. So This is the point that what you do, just because this will give you number of walks of length 1, number of walks of length 2, number of walks of length 3, number of walks of length n minus 1. So you can easily see that if you do the plus, then all entries are non-zero, then it is connected. And if it is connected, then all entries are non-zero. So this is the idea. This method 1 is clear to everyone? Is this method 1 clear to everyone? Please tell me. But let me ask you one simple question. In this method 1, you tell me, but how can diagonal entries, like for this graph, how the diagonal entry will be non-zero? For this graph, look at this graph. For this graph, how the diagonal entries will be non-zero? Like consider this graph. A simple question I'm asking, you calculate m power 1 plus m power 2 because n is equal to 3. So now you tell me in this, how the diagonal entries will be 0? In this one, what will be the diagonal entries? Can you tell me? In this one, what will be the diagonal entries? Yes, diagonal entries will be non-zero because of this. Are diagonal entries will be non-zero because of this, yes or no? Correct? The diagonal entries are going to be non-zero because of this one. So you can easily see that in this one, the diagonal entries will be non-zero because of this m square. So because of this m square, it will make sure that in a connected graph, the diagonal entries will be non-zero. Because this m square, it gives you the degree in undirected graph. So you can easily see if you do the m plus m square, then what will happen? Then this will happen. ABC, ABC, what you will get, tell me? If you do m plus m square, what you will get? So you can see that from A to A, length, walk of length 1, there is nothing. Walk of length 2, there is 1. Okay, from A to B, you can notice from A to B there is 1. From A to C, there is 1. From B to A, length 1 is there, but length 2 is not there. Okay, from B to B, there is 2. From B to B, you can see that there is 2, because you can have this, you can have this. So B to B will be 2. B to C will be 1. C to B, okay, it will be 1, 1, 1. So that's it. So you can easily see that this is connected, and you can easily see that in this, all entries are non-zero. All entries non-zero. So this is correct. Clear? So this method number 1, is this clear to everyone? Method number 1. Very simple method. So in the method number 1, what we do? We just find out the path from length 1 to n minus 1. This is the method number 1. I can say, what is your method number 1? Method number 1 is basically find walks of length 1 to n minus 1. Okay, find the walks of length 1 to n minus 1 in between every two vertices. Between every pair of vertices. So that's it. So this is how you can do it. Okay. So find walks of length 1 to n minus 1 between every pair of vertices. This is what you do. If it is connected, then these values must be non-zero. All the values must be non-zero if it is connected. And if all the values are non-zero, then it is connected. So this is if and only if theorem. So like this. What is the method number 2? The method number 2 is something smart. It is something smart. Let's assume you only want to find a power n minus 1. It is something smart. This method number 2, it uses this idea. The idea is this. See, if you have any graph, like consider whatever graph you want, you can consider. For example, A, B, C, D, consider this graph. Okay. In this graph, what you do? Yes. See, in this is your graph. In this graph, you can notice that do we have n is equal to 4, right? So there is no walk of, is there any walk of length 3? Is there any walk of length 3 from A to D? From A to D. Is there any walk of length 3? Yes, there is walk of length 3. From B to D? Okay, so some other, let's consider some other graph. Maybe you can remove this, or maybe you can remove this. Okay, now also you can notice n is equal to 4. Is there any walk of length 3 from A to D? Yeah. Okay, so you can notice there is no walk. Can you notice there is no walk of length 3 from, or I can say between A comma D? Correct. Why I am taking this 3? Why I am taking this 3? Because this is n minus 1. Okay, this is n minus 1. So you can notice there is no walk of length 3 between A comma D. Now. But there is a walk. Yes or no? You can notice there is a walk. There is a walk between A comma D. Yes, there is a walk, right? Like for example, this is the walk. This is the walk. Okay, so there is a walk between A comma D. There's a walk. Now you can notice if I do this, something interesting I am going to do. What I do, I create this new graph. In this new graph, I put the self loops. In this new graph, I put the self loops. Okay, what I do, I just create the new graph. In this new graph, I put the self loops. Now see, something interesting will happen. Now this walk, you can convert into a walk of length n minus 1. Okay, this walk, you can convert into a walk of length n minus 1. What you can do, you can waste this loop, you can waste this self loop, you can waste, and that's it. That's it. Yes or no? So this is something interesting, that once you put all the self loops, then what will happen? Every walk of G will for if there is a walk in G, then there is a walk of exactly n minus 1 length in G dash. This is interesting. Okay, like what I'm saying that. So this is a note you can take. So if you have any, so you have a graph G. G is undirected graph. Right now, we are considering undirected graph. So G is undirected graph. Now in this G, okay, you want to do from this G, you create a new graph. From this G, you create a new graph. What you do? Put all the self loops. Okay, so what you do? Put all self loops. Put all self loops. You will get a new graph G dash. Now there is this thing that in this G, if there is any path in G, if there is any walk between A comma B, then what will happen? Then what will happen? If there is any walk between A comma B, if there is any walk, whatever walk you take between A comma B, then what will happen? Then in G dash, there is a walk of length exactly n minus 1. There is a walk of length exactly n minus 1. There is a walk of length exactly n minus 1. And this point is actually useful. I will show you how this is useful. So this point is useful like this, that now what you can do, now this is your method, that your graph is this, your graph G, this is undirected graph. Now how this point will be useful, let me tell you. Like this is an undirected graph. Now what you can do to check connectedness, whether it is connected or not, to check connectedness, what you can do, you can just simply do this. Okay, this is the method. First you put the self loops. Tell me, putting the self loops, it means what I'm doing? Putting the self loops, it means what I'm doing? The adjacency matrix is M. Putting the self loops, what it means? It means I'm making diagonal. Yes, I can say put self loops. Put all self loops. And that is same as basically you create M plus IN. M plus IN. Yes or no? This identity matrix. create M plus IN, where this IN is the identity matrix. This is your identity matrix, correct? This is the identity matrix where diagonals are, all the diagonal elements are 1, all the main diagonal elements are 1, all the remaining elements are 0. Okay, now in this matrix, what we need to do, tell me? In this matrix, what we need to do? In this matrix, you just need to find n power n minus 1. No problem. Mavit, if already you have self loop, there is no problem. There is no problem. Now in this matrix, you just find power n minus 1. Okay. In this matrix, you find power n minus 1. In this, if you have all non-zero entries, then implies connected. And if it is connected, then all non-zero entries. So that's it. Isn't it beautiful? Okay. Right now you are thinking this is unnecessary. I know. You might be thinking this is very much, too much, but this is a gate question, Akash. See, whatever I told you, this is just to explain in an easy way, but this is a gate question. Okay, right now you are thinking it is too much. There is no requirement. This is too much. Okay, like too much analysis, too much brain, but this is a gate question. I will show you. This method is the gate question. Okay, Akash, clear? So anyway, is this clear to everyone? See, this is easy to understand. After I told you everything, now did you understand this? Okay, did you understand this now? Tell me. Is this understood? So you can easily see that. So this is the, I can say this is the theorem. This is a theorem that G is connected. Okay, your underrated graph. And G is connected if and only if this matrix has no zero entries. Okay, this is a theorem. And this theorem has come in the GATE exam already. But the proof, did you understand? This proof, did you understand? We have already done the proof. So G is connected if and only if this IN plus A power n minus 1, this has no zeros. This has no zero entries. Clear? Let's move on now. Should we move on? Okay, let's see the next. For the directed graph. So far, whatever we have seen, can you apply on the directed graph? All the things that we have seen, can you apply them on a directed graph? Everything that we have seen, can you apply it on a directed graph? Like for example, connectedness of directed graph, the method number 1, will it work? Will this method work that if you do m power 1 plus m power 2 plus m power n minus 1, it has all non-zero entries, will it work? This has all non-zero entries, will it work? Tell me, will this work? If I say this has all non-zero entries, will this work? Okay, first of all, actually, sorry for that. Because for directed graph, I should not ask you connected, right? I should ask you strongly connected. I should not ask you connected because this connected is not defined. I should ask you strongly connected, correct? Okay, I should ask you strongly connected. This is what I should ask. I should ask strongly connected because remember, for directed graph, connected, disconnected word is not used. Yes or no? Like if you have undirected, for undirected, you can use these words. Undirected graph, either it is connected or it is disconnected. But you can notice the directed graph, this is not connected or disconnected. This is either strongly connected or this is weakly connected, or this is none. Okay, some like none, something like this. So you can see that for directed graph, I should not ask you connected, I should ask you strongly connected. So directed graph is strongly connected or not? What is the definition of strongly connected? Tell me. What is the definition of strongly connected? Strongly connected means what? That means from every vertex to every vertex, there is a walk, there is a path. Okay, yes or no? From every vertex to every vertex, there is a path. from every vertex to every vertex. Okay, there is a path. This is the definition of strongly connected, correct? Do you remember? Do you remember this definition? Strongly connected. From every vertex to every vertex, there is a path. This is the definition of strongly connected. Now, how will you check whether this graph is strongly connected or not? So this method will work. Okay, what you can do? See, if it is strongly connected, you tell me what will happen. If it is strongly connected, then definitely what will happen? If G is strongly connected, then what will happen? Then definitely what will happen? If G is strongly connected, then definitely what will happen? Tell me. Then this will happen that from any vertex to any vertex, what is the worst case, worst length path? Then there exists. Okay, if G is strongly connected, then there exists a walk of length. There exists a walk of length at most how much? Walk of length how much? At most. If it is strongly connected, then there is a walk of length at most n, not n minus 1. Walk of length at most n between any two vertices. Don't take n minus 1 now. Because you can see, for example, A to B, B to C. Now you can notice that you can easily see there exists a walk from any vertex to any vertex. From any vertex to any vertex. From any vertex to any vertex, there exists a so there must exist a length, walk of length at most n, because you can see from A to A. See, from A to A, there is a walk of length 3. Yes or no? From A to A, we have a walk of length 3. From A to A, there is no walk of length less than 3. If I do this, this will be wrong statement. If I do this, this will be wrong statement. Okay, if I do this will be wrong. Because you can notice from A to A, there is no walk of length 2. There is no walk of length at most 2. So you should have at most n. So basically here it will change. The small change will happen. What you do? Plus m power n. Go till m power n. Okay, this is the small change will happen. Go till m power n. Length 4. No, this is not length 4. This is length 3. Length 3. Mavith, length 3. Look, 3 vertices are there. And you can notice this is the walk of length 3. From A to A, there is walk of length 3. Clear? Mavith, is this clear? Let me know. In the directed graph, you can see that walk of length n. You have to go till walk of length n. Please tell me, is this clear? See, here you can see that from A to A, there is walk of length 3. There is no walk of length at most 2 from A to A. From vertex A to A, there is no walk of length at most 2. There is no walk of length at most n minus 1, but there is walk of length n. So you have to go till m power n. Now you can do that. In this, you must have all non-zero entries. Okay, all non-zero entries. In this, if you have all non-zero entries, then definitely it means connected, strongly connected. And if it is strongly connected, then definitely you must have all non-zero entries. So this is the simple thing. This is the simple change. Only this change you have to make. M power n. You have to go till m power n. Clear? Mavit is asking, yes, sir, but we can find connectivity by n minus 1. See, this is not strongly connected. Mavit, this is not strongly connected, right? This is not strongly connected. See, this is not strongly connected. but this is strongly connected. But this is strongly connected. Focus on strongly connected word. Means between every two vertices, whether they are same vertices or different vertices, between every two vertices, you have a path. Is this clear, Mavit? See, this graph is not strongly connected. This graph is strongly connected. Strongly connected means between any two vertices, whether they are same vertices or different vertices, from any vertex to any vertex, you must have a walk. Okay. So you can easily see that in this graph, there is a, from A to A, there is a 3 length walk. You have 3 length walk from A to A. Okay. So that is the reason I am saying that you have to go till m power n, so that you can cover this type of walks. So that you can cover this is what you want to cover. This is the maximum that you want to cover. So you have to go till m power n. So just m power 1 to m power n. If all non-zero, then is strongly connected. If it is strongly connected, then all will be non-zero. Very simple. Method 2, will the method 2 work for the for this strongly connected for the directed graph? Will the method 2 work? Anyone? Anyone? Will the method 2 work for this? For a directed graph, will the method 2 work? Our method 2 that we have seen, will it work? So again, the method 2 will work, but remember, you have to go again till n. You have to do power n. Is this clear? The method 2 will work, but you have to do power n. So the method 2, the same method 2 will work, but you have to do power n. That is the only difference. Okay, so you can notice that what you can do, m plus in power n. This power n you have to do. So I can say this power n, if this has all non-zero entries, okay, in this I can say, in this I can say that if there is no zero, implies strongly connected, and if strongly connected, then no zero. So this is the only difference. You have to do power n. This is the only difference, nothing else. Okay. So now let's see the next point. The next is application number 5. Okay. Should we stop or should we continue? Are these interesting, or are you finding this interesting or not? Actually, these are the gate question. I am just trying to provide you the intuition or the proof. Okay. All these applications that we have seen, these are the gate questions. Already in the gate exam, these questions have come, and they can come. Okay. So, but anyway, now let's see this. Finding the number of 3 length cycles. Let's see this one. Or we can continue in the next class. We can continue. I think this is enough for today. So already these are 4 applications are too much. Okay. So let's continue tomorrow. The remaining 4 applications, four more applications are there. Okay. Total 8 applications. I'm telling you, out of these 8 applications, 4 applications have already come in the gate exam in a single question. Just think about the professor, what the professor was thinking. In a single question, MSQ question is there. In a single question, 4 applications he gave. Of course, that is too much. Okay. So definitely that is too much. It should not happen. Maybe you can give one nice question, you can give on one application. Okay. Right. That will be good. Like what to do, you give one nice question on one application only, so that a student can do the analysis, and student can solve it. But in one question, in a single question, 4 applications, okay, MSQ question, of course that is too much. Okay. So but anyway, we will see this, so that in the future, if some question comes, then you will be able to do. This topic is interesting. Actually, this topic is not complicated. It's just, I can say, you have to think about it. It is something that you cannot by heart. If you by heart all these theorems, like 8 applications, I will tell you, if you by heart all the 8 applications, it will not help you, because in the GATE exam they can give you some 9 application number 9, they can give you some variation. Okay, they can make some changes they can make. So if you by heart these applications, this will not help you. Just understand these applications, understand the proof, enjoy. Okay, because these are interesting. If you, I don't know whether you are finding interesting or not. I definitely find these things interesting. Like, these are analysis. Okay, you are basically doing the analysis, what is happening. Okay, so just enjoy all these things, and after that, whatever question comes in the GATE exam, you can solve it. And one more thing I want to tell you, in the GATE exam, if this type of question comes which is too much complicated, like, okay, then you can skip also. Don't waste too much time in single question. If there is a 1 mark question, don't waste more than 5 minutes. If there is a 2 mark question, don't waste more than 7 or 8 minutes. Sometimes it will happen that you will think that, okay, this is an easy question, I can do it, I have confidence, I can do it. You will solve, and after 5 minutes you will think that, okay, it is taking time. After 5 minutes you will realize that it is taking too much time. It is going, I can say, it is going and going. So at that point of time, you should preempt. At that point of time, you should stop and you should go to the next question. Don't give too much, I can say, bhav. Don't give too much bhav to single question. Okay. So basically, after a certain amount of time, maybe 5 minutes, maybe 6 minutes, if you feel that the question is taking longer, okay, the question is going longer and longer, then leave it at that point of time and go to the next question. Single question cannot ruin your rank. Okay, because of single question, it will not happen that because of that one question I did not go to IIT. It will not happen. Single question will never create, I can say, too much difference, because there are many other questions, as you know. Okay, in the GATE exam, 83 marks means all India rank 1. 70 marks mean all India rank 70. So there are 30 questions, 30 marks of gap. So 1 or 2 marks will not affect your rank. Okay. So, but of course, if you give too much time to one question, if you give 10 minutes, 15 minutes to one question, then in that amount of time, you could have done 4 questions. Those 4 questions will definitely ruin your rank. But that one question will not ruin your rank. So anyway, this type of small things I wanted to tell you. Now, tomorrow we will see the remaining 4 applications. 4 applications that we have seen. Please do them again. Okay. Just try them again. Just try to think about them. If you don't want to think about them, then just leave it, because there is a high probability that next year this question will not come. In the GATE 2023, there is a very high probability that there will be no question based on this adjacency matrix. There is a very high probability, like, because in 2021 question has come on adjacency matrix power. In 2021 question has come. In 2022, 2 or 3 questions have come. Now there is a very strong possibility, almost I can say 99% of chance, that there will be no question in 2023 from adjacency matrix. So that is something you can feel happy. But this topic is interesting. So far, all the analysis that we have done, that is very interesting analysis. Okay. So if you study this topic, then definitely you will find it very interesting. And when you solve the questions of the GATE exam, then you will see that, okay, yeah, basically you will feel happy. You will feel satisfaction that you are solving some nice questions. Okay, some nice analytical questions you are solving. So you will feel confidence. Okay, so that is another point. Okay, thank you everyone. So see you tomorrow. Tomorrow we will see the remaining analysis. Okay.